Okay, welcome everyone. Today's topic is about abnormal curves in Carnot groups. And this topic is, I will focus mostly on geodesics, on Sub-Riemannian manifolds, specifically Carnot groups, but I will define what we call the endpoint map, which is a very useful technique we have to compute geodesics in Sub-Riemannian manifold. Okay, so we start with some preliminaries for Lie groups. So to remind ourselves some basic facts about Lie groups and to define what we have as our main goal here, which are the Carnot groups. Then I will define the endpoint map, which is sort of our main tool here. Then I talk about using this endpoint map, I will define abnormal curves. And then I will remind you of this Pontryagin maximum principle, which we talked about in the past. Leah has talked about it in more detail. I won't go into much detail about this, but I will just mention this theorem because we will use it at the end. And then I will talk about a theorem about abnormality of curves in Carnot groups. So let's begin. Okay, we'll start with some basic facts about Lie groups. So I'll remind you about this adjoint representation we have for Lie groups. So first, we define the adjoint map of a Lie group. And this is, we have a Lie group, we have a Lie algebra, and then we take this map, which maps two vector fields. This map is just called the adjoint map. And we write it as, you see here, it's just AD. And this is this map. And we take two vector fields and map them to their Lie brackets. So this is the adjoint map. And we have the adjoint representation, which is just a map. This is for the Lie group. And this is just this map. It's the derivative differential of this conjugation map, which takes H. H is an element of the Lie group and takes this to G inverse. So this is the derivative of this map. Okay. Now we have the exponential map. What is this? The exponential map is just a map that takes a vector field from the Lie algebra and sends it to the flow of that vector field at time 1. And this has initial conditions at the identity. So this curve, this integral curve of the vector field must satisfy that gamma of 0 equals to the identity. Okay, now we'll mention nilpotent Lie groups. So what is it? A Lie group is nilpotent if we have this descending chain of ideals of the Lie algebra that eventually terminates. So you see here, we have this inclusion. We start with the Lie algebra, and then we call it G0, and then we have this inclusion of Lie algebras that eventually become 0, the 0 algebra. So, and we have this property here. This is not a property. This it must be satisfied. We have this the Lie bracket here must be included in this here. So G of G comma Gi must be inside Gi plus 1. And now we define what we call polarized Lie groups. Now, first, we need to see what a polarization is. So we take a distribution, and the distribution, well, what is a distribution? Well, it's actually a kind of a subset of the tangent bundle of a manifold. Here we have a Lie group, so we'll talk about Lie groups. So it's this subset, and then at each point, we have a subspace of the tangent space, which is part of this bundle, this distribution. And if this subset of the tangent space has the same dimension at every point of the manifold, and here the Lie group, then we say that it has a constant rank. And we call this a polarization. So what is a polarization? To sum up, it's just a subset of the distribution that has constant rank. It's a smooth distribution, a subset of the tangent space, which is a distribution and it has constant rank. Okay, so a polarized Lie group is just a Lie group together with a left invariant distribution. So we take a distribution and we demand that it's invariant under the left translation of the Lie group. Okay, now Carnot groups. Okay, so what is a Carnot group? A Carnot group is essentially a group that admits a stratification. So we take the Lie algebra and we write it as this direct sum of vector subspaces, which is V1. So that's the tensor, this plus here, it's the product Vs direct sum. So these are the vector spaces. And then we demand that it satisfies this relation here, so that Vj plus 1, that's the Lie bracket of Vj and V1. And eventually this will terminate at Vs plus 1. So this will be just the zero algebra. And this gives a grading, this grading here. And we call this a horizontal, we call V1 a horizontal stratum. And what is a Carnot group? Essentially, this is just a group with this kind of grading and stratification. Okay, now that we have sort of the basic understanding of Carnot groups and Lie groups, let's define the endpoint map specifically on Lie groups. Now, the endpoint map can be defined on any Sub-Riemannian manifold, but for the purposes of this presentation, I'll just mention Lie groups. So we say that U is a control of a curve, and it satisfies when it satisfies this property here. So we have that at the initial point, this curve must be the identity of the Lie group, and that the derivative of the curve must be this derivative of the left translation at the point gamma of t times this control here. So a control tells us how to control the curves in a way, how to move, I would say. And this ODE here, this is a differential equation by a theorem by Carathodori. We know that this ODE is well posed, and yes, there should be a D here, not an S. This is a well posed problem. So
can I ask you a question?
Yes.
By well posed, do you mean there is a solution, unique?
Yes, there is a unique solution.
I see. Okay, super. Thank you.
Yeah. Okay. So we also write this curve like this. So here the controls are just the coefficients of the curve. And if xi is an orthonormal frame for the horizontal distribution, we have that the curve can be written like this. So here ui the coefficients, and we restrict ourselves to this curve here. And the initial condition is just gamma of 0 is equal to the identity for the group. Now, the space of controls is an L2 space, and we have this norm for the space. Now, we can define the endpoint map. So the endpoint map is just defined as this, is just a map from the space of controls to the manifold. Now here it's a Lie group. And it's defined like this. We take the control and map it to the trajectory for that control at the point 1, at time 1. And this is the definition of the endpoint map. And we can have a proposition here, we can take the derivative of this endpoint map, which is defined like this. So derivative is just the derivative of this right translation here and the adjoint, the integral of the adjoint. And we can prove this. Okay, to prove this, we need to take a perturbation of the control. So instead of u, you have u plus epsilon v, and that's kind of a perturbation of the control. And we take the derivative of the curve, and that's with respect to the perturbation, so with respect to epsilon, this is a kind of variation. So we take this, and we define it like this. It's just a limit where epsilon goes to 0 of 1 over epsilon times this difference here. And we can use this together with the previous ODE, which is this thing. So if you combine these two, you'll see that you get this ODE here. And we know that the ODE is well posed, so one can check that this thing actually satisfies the ODE. So when we place it, this must be a solution, and we know, since it satisfies the ODE, then we know that this is actually a derivative of the endpoint map. Extended to all Lie groups. There's actually a theorem that can do this. This is Ado's theorem, and it actually holds for all manifolds, Sub-Riemannian manifolds. Okay. So now we defined abnormal curves. Now we have the curves associated with control that are critical points of the endpoint map are called singular or abnormal curves. Equivalently, a curve is abnormal if and only if there exists a covector that satisfies this relation here. So when applied to this adjoint representation of that E1, which is just a part of the frame, that equals to 0. Now we have that the union of all abnormal curves passing through the identity, this is just has measure 0. No, actually, it has measure 0. To put it another way, this is said to satisfy the sad property if it has measure 0. So let's say it in another way. We say that this set, where all the curves that pass through the identity, is said to satisfy the sad property if it has measure 0. So that's the correct way to say. Okay, now let's remind ourselves of the Pontryagin maximum principle. So we have an energy here, which is this map from the controls to R, and this is this thing. Extend this to extend the endpoint map to this space here. So we extend it, we take U to the endpoint and to the energy here. And then we have the Pontryagin maximum principle. Now, I won't go into much detail about this. Ili already mentioned this in the past, but for now, I can say that what I want you to know mostly about this is that what it says that for a geodesic, it can either be a normal or an abnormal. So why is this something new? Because we know that many curves, we actually know that curves don't necessarily can be one or the other. So we have curves that may be both normal and abnormal. So this theorem tells us that for geodesics, at least, we know that it can either be one of the two, but not both. So that's a useful fact for a proof later on. Okay, so we have a proposition. Again, we'll use this at the end. And this proposition says that when we have a step 2 nilpotent group that has a polarization, then we know that there exists a subgroup of this group where gamma, a curve on this group, is non-abnormal. with respect to this polarization. So this is very useful when we try to prove abnormality in curves inside Carnot groups. So we use this proposition as well in the Pontryagin maximum principle. Now we have two conjectures about the Sub property. So remember, the Sub property is about having measure 0. So the abnormal curves having measure 0. So we have the weak Sub property that says that essentially all points that are connected by abnormal minimizing curves have 0 measure, are contained in a set that has 0 measure in the group. And the strong, I should have said strong Sub property here, just says kind of a similar thing, but now we want it to live inside an algebraic subvariety of G. So an algebraic set. And our final theorem, we say that, okay, so let's take a free Carnot group of step 2. So free, we don't impose any conditions here. And then we equip it with the standard Carnot, with the standard Sub-Riemannian metric for the Carnot groups. And then we have the following. First, we know that every geodesic in this group is normal. We will prove this. And second, the strong Sub property holds on this group. And here is the proof. Okay, so we take a curve in this group and make it to be a geodesic. So we have a geodesic that starts at point 0, and at 0, it's the identity, it's the group. So we use the Pontryagin maximum principle, and we know that it's either normal or abnormal, since it's a geodesic. So it's energy minimizing. Now, for contradiction, assume this is abnormal, and then we use this proposition here. We know that there exists a proper subgroup where gamma is actually non-abnormal. So we know that such group exists, subgroup, and we know that inside that subgroup, gamma is not abnormal. Now we can do this. We can identify this Lie group with the Rn, as we see here. It's Rn, and there should be a times here. That's a times this wedge product. This is the space of two forms, essentially, in Rn. And why can we do this? Well, think of it like this. If we take an orthonormal frame in this group, say x1 to, say, xn, then that very much looks like Rn. And then think about the Lie brackets and how they behave. So the Lie brackets of xi, comma xj kind of behave like two forms, right? Because they're antisymmetric, they're bilinear, and they kind of share the same property. So we can do this identification here. And it's actually an isomorphism. So we can write this, and we know that there exists a subspace of R2, such as we have this, we have this from the previous proposition, and this is this thing here. And since we have this subgroup here, and we know this is the curve is not abnormal here, we can just do this thing, extend it to the entire group, and take lambda such that it's 0 outside this H here, which is kind of the normal space. So it essentially proves that gamma is normal, because we take it to be normal inside a subgroup, and then we extend it. And that's kind of the idea of the proof. Now for the second statement, we want the subproperty to hold, especially we want the strong subproperty to hold. So how do we prove this? Again, we use the same identification, and we have theta here for this part, and omega, this is a form here. And we consider this abnormal curve inside the space here. This is this curve, gamma. Now, we know that the curve is, again, contained in a proper subspace of Rn. And we have that it lives here. So we know that the dimension of this V, which is a subspace of Rn, cannot be equal to n. Well, why? Well, the reason is because think of it. So since this is a space of forms, we have that L annihilates the Lie algebra, annihilates the entire group. If n, the dimension of V, would be equal to n, then this would force L to be 0, because otherwise it cannot. It would annihilate everything, the entire Rn, right? You see, because we want lambda to be not 0 by the definition of the covector, and here this would force it to be 0. So we want the dimension of V to be less than n. So now we take this wedge product of omega, which is a 2 form, we take it n over 2 times, and then here will be an even number. And we take this also, this wedge product here, and here omega is just this wedge product n minus 1 over 2, and then here is an odd number. Now we know that both are 0. Why? Well, the reason is because when you wedge more independent vectors than the dimension, then this would force them to be 0, right? And that here we have more than the dimension because we have this property here. The dimension is less than n, and here we have n vectors, so this will force them to be 0. So this proves that both of these forms are 0, and this is exactly algebraic set that we want. This is a set where this is 0 and this is 0. And yeah, that's it for today. Thank you.